and within that, this format of an invited workshop is also new. But I'm very excited about our set of speakers here. And really, the topic of the workshop is what's new and what's old. What's new in computational physics, and what's the same across a huge variety of length scales, going from quantum chemistry, electronic structure, to atomistic modeling, through Hamiltonians, to astrophysics. And what I hope we will learn is that, of course, although the problems are different, some of the attitudes that one needs to take are similar, and maybe, and I don't know that yet, but maybe even some of the techniques. So it already seems clear that symmetry, at least in some of these fields, is really important, and baking in symmetries gets you a long way. So I hope you will enjoy it. We have 2 talks and then a break where we go together to gather our thoughts and talk to our friends. And speakers are, of course, available. And then another 3 talks and another session in Gather to round off the day. So we open with Christoph Ortner, who is an applied mathematician. He's from Austria, did his PhD in England, and his first academic jobs there. And now he's moved to Canada, to UBC. And he's been really, I take credit for making Christoph interested in atomistic modeling, which I think is what is my best move ever. And he's really helped a lot of us put a rigor behind our feelings and to see connections where we didn't see them before. So Christoph, floor is yours.
Thank you, Gabor, for the entertaining introduction. I would say credit or blame, I don't know, but one of the 2 definitely. I had a quick chat with Gabor, what would suit best for this workshop, what I might talk about. Because as you can see, my work in this field is very much with Gabor and also another organizer, Michele Ceriotti. Almost everything I do is somehow based on conversations with them, some papers with them. But anyway, so what Gabor and I thought it would be nice to do is if I, apart from introducing a specific method for machine learning of force fields and interatomic potentials, just try to explain a bit how this is not just a tool for this one job, but much more general, and focus a little bit on this generality, how symmetries can be built into this quite simple and basic machine learning model, actually, that has been very successful for us so far. But I'll still start with interatomic potentials initially, and then I'll move on to other problems and other symmetries. So for interatomic potentials, the context is this: you have an electronic structure model, but in the application you're interested in, you're not actually interested in chemistry, you're only interested in the mechanics. So you're looking actually only at the potential energy landscape or potential energy surface. And so you say, okay, this is ridiculous. I don't want to compute all these electrons. Let me just coarse grain them away. So I define some sort of surrogate model for that. And ideally, I want to compute this surrogate interatomic potential at a cost that is much lower than the exact potential energy landscape. I see this first and foremost as a coarse graining problem, but we all got sort of tired of pen and paper and prefer Python, or in my case, Julia. And so we now sort of augment the pen and paper coarse graining with machine learning technology, and or if in slightly older language, approximation theory, inverse problems, all of that goes into this. Okay, so what does this look like in slightly more closely? Also, the first step that one usually takes, and I'm slightly oversimplifying now, is that you take your potential energy landscape, R, supposed to be some structure, of particles, and you decompose it into site energies. So by this time, so to every particle, to every atom in your configuration, you assign a small energy contribution that depends on an atomic neighborhood. Should have maybe really drawn this. And so you have your configuration, and then to each center atom in red, you draw a circle around it. You say that site energy here may depend only on this small neighborhood, and then you can model that site energy, and that's a hugely important step in build, because it gives you transferability. It means you can train on small configuration and then do much larger simulations, because the site energies are only defined on small clusters, so to speak. Because I will not talk about training at all, I'm gonna skip all these details and only talk about the representation of these site energies. How can we find systematic representations, and how does that connect to machine learning? And so the three main classes, there's a fourth, but I'll come to later, but I would say are these neural network potentials, Villa-Barinello, and relatives, kernel-rich regression methods. This was Gabo's first attempt in this field, and then there are many variants that were developed after that, and linear regression models, which are mostly based on variants of symmetric polynomials. And my talk will be primarily about these, in fact. Okay, so now how does this look like if we get into even more detail? Well, so the first thing one does is one recognizes that site energy has certain symmetries, and the ideal way how you bake that into your presentation is by baking it into a feature vector. And so what is that feature vector? So xi would be the features describing this ith atomic environment. It's some vector in a fixed dimensional space Rd, what could be complex, I guess. So you have d features now describing this atomic environment, and they should be invariant under rotations, permutations, and actually inversions, so isometries and permutations, in fact. So that means if I rotate, for example, this particle system, I get the same site energy back. If I permute atoms in that particle system, I get the same site energy back. And so if you take these features, and we're talking about this, but the talk will be all about these features. So if you can then feed them into a deep neural network, you can use them to define kernels, or in case of linear regression, the features would just become the basis. Then these crucial physical symmetries are baked into your model, and that has huge. So first of all, it's a requirement, because without that you would get wrong physics. But it can have huge advantages and some real challenges that come with it. And this is sort of a bit of the topic of my talk. So I said there's another class of representations that I haven't listed here because they work just a bit differently, but I'll come back to those at the very end. So those are the equivariant neural networks, which are gaining a lot of ground at the moment. Okay. Right, so why do we do this? Well, I keep stealing pictures from Gabo's papers and his presentations. So this is a way to see this. Well, so what you have here is our test errors for a large silicon training set, test set. So on the x-axis, you have various material properties for silicon. It doesn't matter what they are. On the y-axis, you have different potential energy landscapes for silicon, and the z-axis, the error. And the message of this is that all of these different models, old Stillinger-Weber potential, Tersov, and even sort of a tight binding type model, they get very low errors on a small number of these material properties, but not uniformly. So you get, because they're designed to capture specific parts of the potential energy landscape, and the advantage a machine learning approach. So GAP in this case, a kernel-rich regression method, is you can get small errors on all properties. So basically, but because you're using universal approximators, you get to add physics as much as you need to, in principle at least, and that comes with certain costs. So, for example, compared to a Stirlinger-Weber potential, this GAP potential would have about an order of magnitude, would be several orders of magnitude more expensive to evaluate. And so the game now, apart from many other things, is, for example, to lower that cost, to increase how much we can model. And so the model that I've been involved in, that I've been working on with Gabor, and then later with Ralf Trautz also, is the atomic cluster expansion. And so this is, again, this is a linear regression model where these features that we're using are simply a basis of symmetric polynomials. And what we found is really, really nice about this is it turned out to be not just a model for this sort of one thing, fit into atomic potentials, but it's really systematic. You can, whatever symmetry comes up in your problem, you can very easily adapt it. It's very easy to see how to converge it. So what are the approximation parameters and what you need to do with them in order to get convergence. And some of this I want to explain over the next few slides. So this is mostly based on these 3 publications here. And just to, before I do this, I should make a few acknowledgements here. So first of all, Gabor's SOAP descriptor, which then also Michele has done a huge amount of improvements on, is essentially the precursor to that. SNAP, or SOAP and SNAP really, both are. MTP's moment tensor potentials, for those of you who know, are in a way an equivalent representation. Then there's GTINF, group theoretic invariance, is essentially the same idea. And then finally, the NICE framework that Michele's group has been developing is, I would argue, again, essentially the same idea, a very, very nice formulation of these of the basis that we're constructing. So the name is justified. Okay, so the one thing I like about this previous slide that I had here is that we can put ACE onto that, and here's what it looks like. So we basically were matching the gap accuracy. So that's this machine learned potential that Gabor's group has been developing, really on every single one of these properties, and well, we significantly reduce the computational cost on that. And there are actually further improvements that I'm not going to go into. I will only show you really sort of a few glimpses of how well this model works on some simple, relatively simple benchmarks. So just 2 more before I get to, yes.
Is it a good time to ask a naive question just for me?
Go for it.
So this problem of energy prediction, so like the improvements that you are exploring and reporting, are they based on adding more input to the model, or is it just like a better, let's say, transformation of the same inputs? So in other words, because if I understand the introduction, you could, of course, get like a perfect energy, but it would be far too expensive. So you're just looking for like good ways to do coarse graining. Is this more, and so the different models, they decide to focus on different aspects of the inputs, correct? Or is it something slightly different?
You're asking what is the difference between GAP and ACE?
Yeah, so is there a difference in the way in the inputs that they consider, or is it just the way that these inputs are processed?
Not really. So the input is always the same. The data we're training on is always the same, but the representation is different. And maybe the regression scheme as well, but not really, I think, actually. The regression scheme is essentially the same again. So by the way, I should have said this. I will not talk about parameter estimation. I think everybody in this audience understands various forms of parameter estimation. I have nothing interesting to say about it. I will only talk about representation throughout this talk. representation of symmetric properties of particle systems. Yeah.
Okay, and then just to make sure that I understood your answer, is there a sense in which, given the inputs that are the same across all different models, is there a sense of what is the best energy prediction, what one could hope to get with these inputs? So in other words, is the model kind of closed with respect to, can the energy be written as a function of these inputs, or is there some inherent error that all the methods are gonna incur?
So that is a great question, and I could give an entire talk on that as well. So essentially, what you're asking, if I can interpret that, is, have I here, when I did this, did I already make an error that I can no longer improve upon, right? Yes. So there's a cutoff radius here, and basically that is your error. That's your approximation parameter. That is the first approximation parameter we put in. So now, for a material like silicon or other insulators, you can actually prove rigorously, at least for some toy models, not for full quantum chemistry, that such a decomposition does exist. And you can actually write down precisely, qualitatively at least, what is the error you're committing in terms of the cutoff radius. Sorry, was there another question?
No, I think that there was this like EPFL side, they were trying to, I think they managed to complete their setup. So I think it's good. Thank you.
All right. Yeah. So I think your question just says what basically the answer to your question is, this is the first approximation parameter that I should have mentioned. Yeah. And there will be others. Thank you. Yeah, that clarifies it. Thank you. But so this sort of goes back to what I said. It's so this ACE approximation and many others in this actually they are quite interpretable in that way, that the approximation parameters are easy to interpret from a modeler's perspective, and then also easy to tune. Okay, so just very, very quickly, I don't actually want to show results at all, just a few to motivate. So in terms of performance accuracy ratio, this ACE potential does extremely well on a recent performance shootout. It's not a very interesting benchmark for modelers, I think, but just fun to look at. It gets the best accuracy and for very nice performance. That's all to say here, really. And I will talk throughout my entire talk. I will act as if there's only one chemical species. That's almost never the case, of course, and it's just to show that one can do molecules with multiple species, and you can, with this ACE model, you can get in sort of the simplest versions of this ACE model, can get very competitive learning rates. And another, so this was done by a student started with Garber recently, and then there's here's a melting curve for titanium, for titanium aluminum, so you can do alloys. This is not a limitation, and in fact, if you have multiple species, the theory gets easier, not harder. Interestingly enough, but so just bracket that for now and act as if there's all particles are the same. The extension is possible. And so before I now get into describing the ACE model, I want to show something much, much simpler, but that is somehow very closely related. This is something that I think a lot of people would have actually seen in their undergraduate algebra classes, the power sum polynomials. So think of this as really the simplest possible toy model for what we're trying to do here. So assume you have capital N indistinguishable and non-colliding particles on the real axis. So they're just lined up like this. And they're indistinguishable, which means that any property of these particles that you want to compute would be invariant under permutation. So another way you can think about this is, you think of these particles as a set rather than as a tuple. Okay. So the way you can now construct features for this particle system is by just writing down the power sum polynomials. So these here are features that are invariant under permutations of these n particles on the real axis, and what's more, they actually they generate the ring of symmetric polynomials. That means any symmetric polynomial of these n particles you can write as a polynomial of those invariants. that's what they do for. That's the sort of I think the first result that one proves in invariant theory. And what does that gives you has a lot of consequences for us, right? So for example, what it implies is that the mapping from particle positions to this feature vector is injective. So that's hugely important. That means if I know that this feature vector that I've defined here, then from that feature vector, I can recover the structure up to permutations, and the permutations I don't care about, right? So I do want to factor out the permutations. Another property of this is this needs a tiny bit of extra work, but it follows essentially from that is that this feature vector is a local coordinate system. So that means the Jacobi matrix. There's a single exception to that actually. Apart from a single exception, no, actually in this case there's no exception. Always has full rank. That means the inverse of the feature map is a smooth map as well. And that's really important for nonlinear regression when you write some property of your particles as some nonlinear function of your feature vector, because then for f to be smooth, the inverse of x has to be smooth. And the third one is the third consequence of this is that if you take these not just as features, but from these features you can also construct a basis. So namely, if you take products of these features, then all of these products, they define a basis of the linear space of polynomials. Right? So if you take them as features, then you can use them to generate the ring, but if you want the linear regression scheme, that you need a basis, and you can construct that as well simply by taking the products of these. So basically this contains everything. So every single property you might want about these features is in there. And so the question now is, right, so I don't have 1D particles, I need to have 3D particles, and I don't just have the permutation group, but I also have the rotation group. And what happens now? So and that's the next step of my talk. Okay, so so here's how you go about this. You form what we call the density projection, and those are precisely generalization of these power sum polynomials. So the way this is usually motivated is you first take the particles that you have at relative positions Rij, right? Those are the particle positions in an atomic environment. And then you write down the density of the particles in this atomic environment, and then you project that density onto some basis. So typically, the way you would use this, you construct this basis is you write it in terms of sort of polynomials in radial coordinates times some spherical harmonics. So they remain polynomials overall, right? Which is nice. That's not a necessity, but let's assume that for sake of simplicity. And so that in fact gives you features that, and if you take sufficiently many of them, if you take these polynomials to sufficiently high degree, they are complete features. That means that they fully specify your atomic environment again, but they are only invariant under permutations, and of course not under rotations and inversion. So now, how could you make them invariant under rotation? Say, well, you just average them, right? So if you take these features and you average them over all rotations and inversion over the group of 3, so then unfortunately what you end up with is with features that where the sort of the angular information is just gone. It's integrated away. So you end up with features that have only radial information left. And from those, you cannot recover the first thing about your atomic environment. You only know how far from the center are the atoms, but you don't know how they relate to one another. Okay, so this is sort of a little bit related, and as I go along, it will get closer and closer related to what is called the phase recovery problem in signal processing. So one technique to go about that in signal processing is exactly what we do here as well. So instead of symmetrizing these density projections, the one correlations, as we call them, of this density, we symmetrize the n correlations. So what we do is we take n correlations of the density, we project them onto tensor products of that basis, and that can be very conveniently written simply as products of these one correlations. So of course, they're still not O3 invariant, but the point is that now when we symmetrize them, we integrate over the second part of the symmetry group, then we end up with non-trivial features. Whereas for one correlations lose all their angular information, these n correlations don't. They retain some of it. And how much of that they retain, that's sort of the huge challenge here to understand, and just to say we don't. But we use them very effectively. Okay, and so now there's one more comment to make here. This looks like a nasty thing to compute, and you wouldn't in practice, right? But because you have the spherical harmonics here in the basis, that allows you to resolve that integral explicitly, and at the end you can express that operation. So going from these n correlations here, that they're grouped here into a long vector, to symmetric features that are fully permutation and O3 invariant now. It's just a linear operation. It's a multiplication with a sparse matrix. That's what this here leads to. One can pre-compute this very effectively. And just maybe there's one comment to make here. The nice scheme that Michele's group has been developing, this is a scheme to do the same thing, but in a sort of recursive way. Okay. One needs to be a little bit careful here, but it's almost a triviality once you realize that you do, and then you can, with this construction, you can very easily obtain a basis for the space of polynomials that are invariant under permutations and under O3. And I think I'm going a little too slowly, and that's why I'm going to skip this. But just to say the usual candidates, power spectrum, bispectrum, are all in that class. Okay, so I now need to talk to Gabo quickly because I want to know when you want me to stop, how many minutes you want to give me from here on.
3. We started a few minutes late.
Yeah. So what I'll do is I'll state the main things very quickly. So first of all, with the construction I've given you, and this is almost trivial, that statement, what you get is a spanning set of all polynomials that are invariant under permutations n of 3. And it's very easy to reduce this down to a basis, but one has to do it numerically. So this is a bit of an issue. So now the second thing, because you have spanning set, you can now identify what are the approximation parameters. So I already mentioned the cutoff radius, the polynomial degree, and then there's another one in there, which is the correlation order, which tells you basically in these n correlations, how high is the correlation order in there that you have chosen. And in those 3 limits, you can represent any smooth side energy. And then finally, this is a little result that I'm quite fond of, which is that you can evaluate these models that you've constructed that way at a cost that is very close to optimal. But I won't go into details here now because I'm out of time. Okay, so I will skip that as well. Just to say, if you treat these ACE features not as a basis, as a linear basis, but as features for nonlinear regression schemes like neural networks or kind of a rich regression, then there is a huge number of open problems, a huge number of things we do not understand about them. And I think that we can very happily discuss them later. Okay, but so the main thing now is that I promised I would mention is, there are lots of symmetries, right? So there are lots of problems on this scale here, right? And all of them come up. You have different kinds of properties of the particle system that you want to represent, and they all have different sorts of symmetries. And you might want, for example, to fit a Hamiltonian matrix and represent a Hamiltonian matrix, and then you have sort of a covariance. You might have a non-conservative force. I don't see that in here, but it could be. And then you have a covariant vector, right? You might want a friction tensor. Then you have, again, you have covariant matrices, but a different sort of covariance than for Hamiltonians. And so I'll just, so now in the last 2.5 minutes, I will say, what does ACE look like when you do that? And it's very straightforward. So first, what you need to do is you need to specify what are how your particles defined, right? So before I said they have a position, but now they could have positions and all sorts of other features. They could have a magnetic moment. They could have a dipole moment attached to them. They could have a charge attached to them. They could have a magnetic moment attached to them, right? Whatever you wish. And then you have a property that you want to compute. And that could be an invariant property of your particles, but it could be an equivariant property, a covariant property, right? So all you have to do is you have to specify what is your symmetry group, what's the action, and this doesn't have to be O3. It could be a different symmetry group, right? And then you specify what is the action of your symmetry group on your states, what is the action of your symmetry group on your property. Right, and so invariant scalars we've covered, right? Here's an example where particles have additional attributes, right? And so then the action of the rotation group on this pair would be the action only on Rj. Qj is left invariant. Here's an example of a covariant vector, right? So now the action of the symmetry group on the property would be the rotation of that property, right? Because it's a vector now. It could. This is something that Michele mentioned at some point to me that you could have. I think they're called pseudo vectors, right? That the vector doesn't follow the inversion correctly, and I can keep going, right? So I mentioned friction operators. Those are again, those are covariant. They are built from covariant matrices. Hamiltonians, they're also covariant matrices, but now the action of the symmetry group is no longer with the rotation matrix Q itself, but with the Wigner D matrix. You can have different symmetry groups, right? So maybe one example that I'm working on right now is if you want to model magnetism without spin-orbit coupling, then you have two copies of the O3 rotation group, so now you have to look at what is the action of two rotations on a position and on a spin, and the first rotation is applied to the rotation, the other to the spin. And it keeps going, right? So you start making lists, and suddenly you see related, similar symmetry groups all over the place in all sorts of other applications. And so then the question is, what would this ACE model look like in that case? Well, one thing that all of these particle models should have in common is the permutation invariance. Yeah. And that means the first two steps are the same, right? So the density projection part, that remains the same, and the end correlations, they also remain the same. Nothing changes here, right? And it's only the symmetrization step. That's the only thing that will change now. So this integral that I've written here, what does that become? You simply replace O3 with your symmetry group. Then here you have the action of the symmetry group on your particles. And then you have to put in the action of the symmetry group on a basis in property space. So for an invariant, it's just a one, that's the basis, so nothing happens. But if this, for example, were a covariant vector, then all you have to say, what is the action of the symmetry group on a basis for all these vectors? And then you need some efficient representation of that averaging, of the symmetrization. And for the majority of all the symmetry groups I've mentioned, there's basically an immediate generalization of what I've shown. There are Clebsch-Gordon coefficients for these symmetry groups, but in general, it's not clear at all. So if you're trying to go to arbitrary, even Lie groups, as far as I understand is, there is no such thing. So my understanding is,
can you wrap up
at the moment?
Half a minute or so.
Will do. All the theory applies that I've shown you for invariant ACE. Everything goes verbatim without any changes. Okay, right. So this was the last slide I was going to cover, but I'm happy to skip this. Maybe the simple comment to make here is that I've obviously been chatting too much. Sorry about that. The comment to make is that I've shown you how to construct a linear model that has a huge amount of flexibility, that is systematically generalizable in a very nice way. But of course, what you can also do, and this is exactly what we are starting to do nowadays, is that we don't use it as a linear model, but rather to use it as a component, as a very flexible model component for nonlinear models. But exactly where this is going and how this is going, I think will emerge over the next year or so. All right, so I'm going to stop here, and maybe just to emphasize one more time, I've not been talking necessarily about my own work here, but about the work that a lot of people have done, including especially Gabo and Michele and Ralf Trautz, and I'll leave these points here for discussion now. Thank you.
Thank you, Christoph. I'm suggesting that in the interest of keeping somewhat on the schedule, that we take questions in the Gather meeting. That will also encourage some of you to come to the Gather Town link. And let's go to the next talk. Can you unshare, Christoph and Julia?
Yes, so